Today we're going to talk about exponents. And what we've been working on so far is we've been working with linear functions. And linear functions have a constant value in them. They grow by equal differences over equal intervals. And now we're going to move into exponential functions, which grow by equal factors for equal intervals. And before we can really get into the exponential functions, we want to go back and refresh our memory on what do we do when we're working with exponents. And I'm going to say that I will probably do more work than you want for these, but I really just want to get these rules back in our head. So first and foremost here, we got this chart here. The following sequence shows powers of 3 by repeatedly multiplying by 3. And typically, the ones that I have filled in right now, 3 to the first is 3. 3 to the second is 9, and all that we did to get 9 is we multiplied our previous value of 3 times 3 again. Well, if we want to figure out what 3 cubed is, then what we need to do is we need to multiply by 3 again, and we get 27. And just to digress for a minute, 3 to the first means 3 times itself one time. 3 to the second, or 3 squared, means 3 times itself twice. 3 times 3. 3 cubed means 3 times 3 times 3, which is what we have here in our chart. 3 times 3 gives us 9, times 3 gives us 27. Typically, if we have issues, it's when we go towards the left in this chart, which is if we're multiplying when we go right. What operation do you think we're doing when we go left? Division. So if we go backwards here, 3 divided by 3 is 1. And that is true. 3 to the 0 is 1. 1 divided by 3 is what 3 to the negative first equals. That is true. 3 to the negative second is 1/9. It's 1/3 divided by 3. And then 3 to the negative 3 is 1/9 divided by 3, which is 1/27. What we need to take maybe a closer look at in terms of refreshing our memories here are these rules, and I highlighted these, and I'm not much of a highlighter, but this pattern can be duplicated for any base raised to an integer exponent. So that means a positive number, a negative number, 0, no fractions, no decimals. But what we have in terms of our definitions is if we have b to the nth power, it just means b times itself n times. How many n's do we have? B times b times b. So if we have b to the 10th, we have b times 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 b b times b. We just have 10 b's multiplied together. B to the 0 equals 1. That's one of those obscure rules that you may or may not know. If you know it, good. If you don't know it, star it, that's something that you need to go back and study. And then here is the one that I really do want to look at, which is b to the negative n power. And what b to the negative n power causes us to do is it causes us to have a fraction. As you can see, this is 1 over b times itself n times. The way I like to describe it is, I like to say that when we have a negative exponent, we flip this and we change the sign on the exponent. So b to the negative n is the same thing as 1 over b to the n. In contrast, we also could have had 1 over b to the negative n. And again, with the negative exponent, what we do is we flip this. And when we flip that fraction, so it's b over 1 now, then our exponent changes the sign. So it becomes b to the positive n. And we're going to work with this throughout our notes here. But we're going to start back again to simpler days. In the first example, it says, write each of the following expressions as repeated multiplication. Well, 3 to the 4th, b to the n. This just means 3 times 3 times 3 times 3. Repeated multiplication. 2 to the 5th, 2 times 2 times 2 times 2 times 2. 2 multiplied by itself 5 times. Over here, the 4 to the negative 2, we need to go back and look at our rule. And b to the negative 2, or 4 to the negative 2, means that we're going to flip and change the sign on the exponent. It was 4 over 1. And then if we write it as repeated multiplication, this becomes 1 over 4 times 4. Maybe it takes you back to your Algebra 1 days. Now, problem number 3. We're given this function, f of x equals 2 to the x. We want to evaluate each of these functions without using our calculator. And we're going to show our calculations. So again, I may be showing way more work than you. But the first one is f of 2 equals 2 to the x. Remember what's happening when we're working with our function. We're going to take 2, and we're going to put it back into our function wherever we see x. So this is going to become 2 squared. If we use our repeated multiplication, that is 2 times 2, and 2 times 2 equals 4. Maybe you need to show all that work, maybe you don't. Letter B, f of 0. We're going to put that value back into the function 2 to the x. In this particular case, we're going to take 0. We're going to put it back in here for x. So this is going to become 2 to the 0. And what does any number raised to the 0 power equal? It equals 1. Over here in letter C, f of negative 2. We're taking this value, negative 2, and we're going to put it back into the function wherever we see x. So we're going to take this negative 2 and we're going to put it back in here for x. So this is going to become 2 to the negative 2nd power. Again, with the negative exponent, we flip and change the sign on the exponent. It's going to become 1 over 2 squared. And we already know what 2 squared equals, but just to show the work here, 2 times 2 is our extended multiplication. And we know that 2 times 2 is 4. So 2 to the negative 2nd is 1/4. Those negative exponents oftentimes lead to a fraction. As we flip our paper over, we are getting close here. There's many properties or laws that are important, but we're looking just at a select few exponent rules. So now, if we flip our paper over, for each of the following, we want to come up with the rule, and some of you still might remember from Algebra 1 what the rules are, but if you don't, we can figure them out. So it says, for each of the following, write the product as a single exponential expression. Write A and B as extended products first as necessary. And when we start our first one here, we've got 2 cubed. And 2 cubed is 2 times 2 times 2. We have 3 as our exponent, so we're going to multiply 2 by itself 3 times. And then we have 2 to the 4th. 2 times 2 times 2 times 2. Well, we don't have to figure out what that actual number is because our directions say that we want to write it as a single exponential expression. So we're going to have an exponent in our answer, but how many 2's did we end up with? And we ended up with 7. 1, 2, 3, 4, 5, 6, 7. So 2 to the 3rd times 2 to the 4th is 2 to the 7th. We can do the same thing here with 2 to the 6th times 2 squared. Oh, 1, 2, 3, 4, 5, 6. 2 to the 6th times 2 squared. Again, we want to write it as an exponent. How many 2's did we end up with? Well, 1, 2, 3, 4, 5, 6, 7, 8. 2 to the 8th. And I know there's not very many examples there, but what is the rule when we multiply terms with like bases? We add the exponents. So this is going to be 2 to the m plus n. And notice, we didn't multiply all the 2's together. We kept the base and we added the exponents. So the question is, we were working with positive exponents here. Does this rule work for negative exponents also? So let's try and figure out if it does. We have 2 cubed times 2 to the negative 1st. It says, use the exponent law found in exercise 3C to write this as a single logarithm. Well, what we just did is we said, well, when we multiply these two together, 2 cubed times 2 to the negative 1st equals 2 to the 3 plus negative 1. We added the exponents together. And when we add those exponents together, we get 2 squared. And by the way, do you remember what 2 squared equals? We've already done it multiple times. And it does. It equals 4. Well, let's do on part B here. We're going to evaluate 2 cubed times 2 to the negative 1st by first rewriting 2 cubed and 2 to the negative 1st, and then simplifying. So 2 cubed is 2 times 2 times 2. And 2 to the negative 1st. 2 to the negative 1st, once again, we can flip and change the sign on the exponent. So we're going to flip and change the sign on the exponent. And then we want to simplify. Well, those blue 2's. 2 times 2 times 2 is 8. 1 over 2 to the 1st is 1/2. And what does half of 8 equal? Half of 8 is 4. So when we look at part C, do our answers from A and B support that rule applies to negative exponents? And it does. And I want to write a little bit more here. But yes. We add exponents. Whether they're positive or whether they're negative, when we multiply terms with like bases. Again, it doesn't matter whether the exponent's positive or the exponent's negative. We add the exponents when we multiply. One more property to look at. So one more. For each of the following, write the exponential expression in the form of 3 to the x. Write a and b as extended products first, if necessary. And I'm going to write them as extended products. But what we have in this first problem, part A, is 3 squared cubed. So 3 squared means 3 times 3. There's an extended product. But then we're going to cube that. So if we want to write it out longhand, and again, I might be doing more work than you need. This is 3 times 3. This is 3 times 3. And this is 3 times 3. There's 3 squared cubed. As we take a look at this, how many do we end up with? 6. Let's try another example here. 3 to the 4th. Well, 3 to the 4th is 3 times 3 times 3 times 3. And we're going to square that. So squared means times itself. So I need to separate this out a little bit. So we get 3 times 3 times 3 times 3. There's 3 to the 4th once. Here's 3 to the 4th twice. And how many did we ultimately end up with? We ended up with 8. Again, it's just a quick couple of examples, but can we determine what that rule is when we do these kind of problems here? Well, if we go back and look at the exponents, we had an exponent of 2 and we had an exponent of 3. When we finished, we came up with 6. When we started, we had an exponent of 4 and an exponent of 2, and we ended up with an exponent of 8. What process did we have to do to get that 6 and that 8? What? We had to multiply. So when we look over here, what we're going to do is we're going to take those two values and we're going to multiply the exponents. I oftentimes refer to it as superpower. We superpower the exponents. So you know. So to finish, consider this expression, 3 to the negative second raised to the 4th. Show that this expression is equivalent to 3 to the negative 8 by first rewriting 3 to the negative second in fraction form. So let's follow the directions here. 3 to the negative second in fraction form. We flip and change the sign on the exponent. So this is going to become 1 over 3 squared. And that looks like a negative there, so I'm going to rewrite that. It's not. It's 1 over 3 squared. There's 3 to the negative second in fraction form. And we're going to raise that to the 4th power. So if we use our extended multiplication, we get 1 over 3 squared times 1 over 3 squared times 1 over 3 squared times 1 over 3 squared. And we can even write that out a little bit more, and again, I know I'm writing more than some of you need to. But this is 1 over 3 times 3. And 1 over 3 times 3. And 1 over 3 times 3. And 1 over 3 times 3. Well, how many 3's did we end up with? As we count them, 1, 2, 3, 4, 5, 6, 7, 8, we get 8. Notice that that's 3 to the 8th is still on the bottom of the fraction. But if we want to compare here, it says show that this expression is equivalent to 3 to the negative 8, remember, we can flip this and change the sign on the exponent. So this would become 3 to the negative 8 over 1. If we flipped it and changed the sign on the exponent. And lastly, it says show that this equivalent show that this expression is equivalent to 3 to the negative 8. Well, we had 3 to the negative second to the 4th. Remember that we can superpower this, and negative 2 times 4 is negative 8.